Welcome. This is one of 2 COSIC seminars happening in a row. All of the recording equipment is fucked, so you are stuck with me being very seated and stationary. I'm sorry. This talk is on a paper called Finally, written by myself, Zajonc, whose name I've spelled wrong for the 15th time in the last 12 months, and Barry. And it's about bootstrapping LWE using NTRU, or a bunch of keys and noise which have been a pain in my ass for the last 12 months. Quick disclaimer, notation in this presentation has been simplified to the point of being incorrect. Do not try this at home, don't pass go, do not collect $200. Read the paper if you actually want to do this shit. So first off, what are we doing? Well, we are using NTRU-based encryption to bootstrap LWE-based FHE. Why are we doing this? Well, it has less key materials than some alternatives, and also it's fast enough to be good. And if you're asking, well, wait a minute, didn't this paper called Final already do that? Well, yes, but we add a second key, and possibly a third key if you're willing to stretch the parameters a little bit. That was a lot of acronyms. So first off, for those of you unaware, FHE is fully homomorphic encryption. The long and short of that is it's encryption that you can perform operations on and still have your message make sense after you decrypt it. NTRU stands for Number Theorists Are Us, which is a fun fact that I learned in a different COSIC seminar. Come to these, they're, you know, informative sometimes. And it is a type of problem on which some encryption schemes are based. LWE stands for Learning with Errors, a different encryption scheme. This is the one that most FHE is based on. And Final, which is a paper I've mentioned, is Faster FHE instantiated with NTRU and LWE. It does roughly the same thing that we do, except using exactly one key. This is the rough structure of both the paper, the encryption scheme, and also this presentation. As you can see, it is a slight mess. We start off with LWE all the way in the start. We have a nice ciphertext under the LWE scheme, and we have to go through some bootstrapping to make the noise suck less. But in order to get that to happen, there are many steps within the bootstrapping, and also many things that those steps require me to explain, hence the complicated diagram. We'll start with the most basic of basic things and go with LWE first. So we're first going to go with multi-key LWE encryption. The key generation is relatively simple. Bit string. Create a bit string. That is now your key. Your encryption is then, you'll notice there are a bunch of zeros in there. Those are for other people, but you generate a public parameter, which is the vector AI that you see in there. And then based off of that, you compute the quote-unquote actual ciphertext B, which is your public parameter, dot producted by your key, and then you add delta, which is just a value we put in there to make rounding look nice, your message, and then some small error to make things vaguely secure. And decryption is basically, well, you subtract the AI and the SI, so the public parameter and the key, and you round. And you divide by delta first, and then you round, and you hope that that your error divided by delta is small enough that it doesn't break your whole system. Managing that, that error is the whole point. So in order to do that, we bootstrap to keep the error low. The main operation, besides just XORing things together, is the NAND gate. I'm not explaining how that works, but that's how you do basically every single operation in practice. How does multiple keys work? Well, every key just gets its own public parameter in its own slot. So if you were to add 2 of these together under different keys, and so with public parameters in different spots, you just put them in different spots together, which means that when you decrypt, you now decrypt by using each public parameter multiplied by its specific key, and those all round away, and everything else stays exactly the same. Moving on to the other thing we're doing, you'll notice this says NGS and not NTRU. That's because things are complicated, and NGS actually stands for NTRU-based GSW-like scheme. So if you know GSW, this may look somewhat familiar. If you don't, it still will look unfamiliar. Key generation, this is already simplified. It's basically a polynomial. You generate a polynomial until some things are nice, until some specific properties are nice, and preferably with ternary coefficients. Then there are two kinds of encryption, just to make things extra fun. There's the scalar encryption, where this whole thing is a single polynomial. So we generate some noise g, so this g takes the place of the e in the LWE encryption. We divide that by our key, we add delta and m. There's also a vector encryption. This thing is now a vector of polynomials, and we take g, we make that instead a vector of random small polynomials instead of just the one, divide all of those by fi, and then add this g, which I will explain in a minute, times m. The reason we have both of these is because of the main operation, the reason we like the NTRU encryption so much. We never decrypt this, so we don't bother. It exists only in bootstrapping. We key switch over to an LWE encryption from our NGS encryption, so decryption doesn't exist. If you wanted to actually decrypt this, you would multiply by your key and round, basically. Multiply by your key, divide by delta, round away, and just hope that g divided by delta is small enough. The main operation is the external product, which I will get to in a second, but first, a word from our sponsor. This COSIC seminar is brought to you by gadget decomposition. Have you ever wanted to just represent a number as a vector with just all of its digits in it in proper spaces? Well, now you can. Try gadget decomposition today. You choose two numbers. One of them is your modulus. One of them is your base. You generate some L, which is just the length of the vector we are now generating, and voila, the gadget vector, which is just your base to all of the possible powers. And now you gadget decompose. So you take a number, you multiply this by the inverse of that vector you just generated, and now you have all of the digits of your number neatly arrayed in a vector just for you. So, of course, this is invertible. So if you gadget decompose something and then multiply it by your gadget vector, voila, your number again, as if by magic. So as an example, if we choose our modulus to be 100, we choose our base to be 10, you know, things we like to do, then the length of your vector is obviously 2, and your gadget vector is then 1 and 10. So if we take 15, we gadget decompose it, then we get 5 and 1 because that's the order our vector ends up in. Very simple. Ask your cryptographer if gadget decomposition is right for you. There are some side effects. Don't worry about them too much. So using this gadget decomposition, we now have a nice, neat thing called the external product. It basically lets us multiply two messages together using two ciphertexts, and the main thing to note about this whole thing is that it requires both a scalar encryption and a vector encryption, and then it returns a scalar encryption. So you basically use up vector encryptions as you keep using this thing, which means that its use is very limited because all of your things have to happen in the correct order, and once an encryption has gone through it, it can now no longer be used again because you need another vector encryption, and you have to create new ones constantly. So this basically causes the entire order of the whole bootstrapping procedure, because you need to keep going scalar, then another vector encryption, then another vector encryption, and so on forever. The gadget decomposition is in there because if you remember from earlier, which I'm not going to go all the way back to, our vector encryption had the gadget vector in there in front of the message, and so we need the gadget decomposition in front of our first ciphertext just to make sure we have something which just has delta times the two messages. And that will become, you know, our new message in our new scalar ciphertext. What about multiple keys in multi-key NGS? Well, unlike LWE, it doesn't have to expand, so you don't have a new public parameter that needs to be in a different slot in your vector for each possible key. You just pretend everything is a single key NGS ciphertext under the product of the keys. Now you'll notice that this makes our noise, which was originally just a single polynomial g, it is now the sum of two products of polynomials, which is bad, because that's real big. So this is going to be our main limiting factor for the whole process, because we're going to have to multiply these together, and then suddenly our noise grows exponentially, which, not good. However, it is just like a single key ciphertext, so no matter how many of these keys we add, assuming the noise doesn't kill us instantly, it stays the same size, which is nice for storage purposes. So, I mean, I've given the game away a little bit with the noise thing, so in order to make that noise work, you would need larger and larger parameters to make it fit, which sucks by itself, but if it's so good, why aren't we just doing that? Well, in 2011 or 2012, they tried that already, and there was a multi-key FHE scheme based off of NTRU, and it was broken within like 5 years. And then the attack was made even better, and then in 2021, they were like, this is the exact point at which your parameters become too big, and the whole thing is broken. So using large parameters in NTRU is really bad, which is why we're keeping it to just the bootstrapping. It is nice and fast in short bursts when we can start and end immediately, get out of NTRU before things get really hairy. Which is also the reason that all of the FHE stuff is using LWE these days and not NTRU, because big parameters bad, and you kind of need big parameters to make your noise not suck. So, moving on to the bootstrapping, briefly how this is going to look is we are going to transition from an LWE ciphertext to an NGS ciphertext roughly of the LWE encryption, give or take. Then we're going to do some monstrosity called the blind rotation, which I'll quickly go over, to homomorphically decrypt, so now we have an NGS ciphertext of just the message. We'll key switch from an NGS ciphertext to an LWE ciphertext, and then because NGS and LWE use different parameters, we now have to also mod switch to make everything work nicely together. So before we do that, we now need to do blind rotation, and before we do blind rotation, we now need the cryptographic multiplexer gates. So these are essentially just a cryptographic multiplexer gate. It is exactly what it says on the tin. Why we care about these is not so much this nice diagram. It actually has a nice property where if you have an LWE encryption and you do notation fun, and you use the correct key as your side input, or your correct, it's not even the key, it's the correct bit of the correct key as your side input, and you line everything up nicely, you get vector encryptions of parts of your LWE message, like decryption. So as you can see, you get a vector encryption of x to the CISI, and so if you look at this very nicely, then you just multiply these together. It's real easy. You just multiply these together, and you'll notice that that sum looks an awful lot like your LWE decryption, which is secretly what we're doing. Now the problem is, how do we get it out of the exponent? And also, how do we multiply all these together? They're all vector ciphertexts. Well, that's what the blind rotation does, except that instead of doing it in the order that kind of would make sense intuitively, in the sense that you do all the CMUXs, you multiply them together to create, x to the decryption, so you basically get x to the m plus your error, and then making that, instead of x to the m plus your error, making that just a ciphertext of m with the message m. We now have to do things kind of backwards. And so after many of your CMUXs, you get something that looks vaguely like this, and actually this is just x to the m with shenanigans. And now we do shenanigans. And you'll notice that this is in entirely a backwards order, where we do a whole bunch of nonsense first, then we add all our CMUXs in there, and then we do a slight correction. And the reason for that is we need a scalar ciphertext to start out, and then we can multiply all the CMUXs on there, which are all vector ciphertexts. So the whole thing is a little bit backwards. All of this is a lot of algebra. Don't try to read it too hard. It will make you cry. And then we end up with a scalar NGS ciphertext of m under our key, which is in fact just the multiplication of all of the other keys. Then we need a key switch. Key switching is relatively simple. It works like every other key switching in existence. You make an encryption of the new key, or of the old key under the new key, and you do some nice things to make all of your error terms go away, and now you get an LWE encryption of your message. This isn't the terrible part. The terrible part is you'll notice that our key switching key is an LWE encryption of the product of everybody's NGS key, which is bad, because now we need to do a whole bunch of LWE multiplications, which requires a metric buttload of NAND gates without bootstrapping, because we need this to do the bootstrapping. So, key switching key generation. How do we do this? Well, key switching key is, product of all of those. How do we get this? Well, there's a neat thing called a hybrid product, which is a lot of algebra and is long and boring, but the thing we care about is this nice property. We're going to skip over the part where we have hybrid product keys, because generating those is trivial. We're also going to skip over the fact that the hybrid product actually has steps that you execute in order to do the hybrid product, and we're going to pretend it's a magical thing that everybody knows how it works, because I could be here for half an hour otherwise explaining it. The long and short of it is, we take ring LWE, don't worry about it, it's LWE in rings, and we leave the zeros that we need, and we just make sure that we start with the first key in the first slot. And every time we hybrid product with the correct hybrid product key, which is basically an encapsulation of the next NGS key that we want to multiply on there, we hybrid product. Now we have one extra public parameter in there, and our message now is multiplied by another extra key plus some more noise. The amount of noise this generates is bad in the sense that this is our biggest amount of noise that we generate within NGS, because you will end up having, or sorry, the biggest amount of noise that we generate within LWE during the bootstrapping, so this is the biggest part of residual noise. However, it's still fine. You can still then perform a number of NAND operations before you need to bootstrap again, and you also only have to do this monstrosity once, because our key switching is basically doing a bunch of these hybrid products in a row to create the key switching key, because you need to do this once for every NGS key. Right? Very complicated. Long and short, multiplying on another NGS key is just doing another hybrid product operation, which sucks, but works. So then modulus switching is very trivial. You do a randomized rounding function, and then you call it done. You have now mod switched. Congratulations. That's most of it. So you now LWE, you do your conversion using the CMUX gates. You then blind rotate so that your message is now actually the message and not just the exponent of the message. You key switch to make it LWE again, and now you mod switch to make it the LWE in the parameters that you actually want. Now, using NTRU is fast, and I will get to how fast that is in a second, but remember how I said that big parameter is bad, and also how noise in NGS grows with the number of players by the number of players? This table has a lot of things in it. On the very left, the capital N and the capital Q, those are your parameters for your NGS. The small n and small q are your parameters for LWE. Your epsilon is some other parameter that we have to pick, which I cannot remember this second. And Kmax is the maximum number of players that each of these parameter sets supports before the whole thing breaks, because you have too large noise in your NGS. Now, with relatively normal parameters, read the parameters that they used for single key final, you get 2 players, which is you, a friend, and also that server that you're doing all your computations on. This is fine for some applications. If you want more, then you have to grow the parameters and then grow them further. And at the bottom of the table, you'll notice that the error rate has suddenly spiked to 1 in 2 to the negative 30. And the reason for that is putting parameters any bigger than this breaks the program that we were using to estimate the error rate. So you probably don't want to use those if you're doing this practically. Basically, very limited number of players that we accept. Other than that, we're faster than MK-FHE. Our key material isn't ridiculous, but you'll notice that the number of polynomial multiplications per bootstrapping that we have to do is linear in the number of players, because the number of players is k, because small n is already taken, but it's linear in the number of players instead of quadratic in the number of players. So that's our nice contribution to FHE society. Yeah. Are there any questions?